past couple of years have been master classes in all kinds of things, computer science, from massive data replication technologies and techniques to database technology at a core level. Always great talk. Can't wait to hear what Werner has to share today.
Have you ever thought about the world? All of its goings-on? How chaotic it might be? You probably see it when you get your coffee, or when you turn on your laptop, or when you detangle all of the wires underneath your desk.
Oh, of course. I often say the world is asynchronous.
Now imagine a world that is ordered, synchronized, one by one. Would you like to see that world?
Nope.
Where's your sense of adventure? Look, if you take the blue pill, our story ends here and this conversation never happened. If you take the red pill, I'll show you a more ordered world, one that is synchronous.
What about the yellow one?
Oh, that's just a jelly bean. Banana. All I'm doing is offering a simulation.
Here you go.
Thank you. I'll need a minute.
Oh, take your time.
Burger and fries?
One at a time, please, sir.
Burger?
Hey, Ryan, welcome.
Thank ya.
You haven't missed anything yet.
Anything else?
Fries?
Excellent.
Matrix earlier.
I think I've eaten at this restaurant.
French fries.
This place is crazy.
No, this place is synchronous.
Well, this place sucks. And how did you get that so fast?
That's not how, but where, shall we? It's for you.
Please welcome the Vice President and Chief Technology Officer of Amazon.com, Dr. Werner Vogels.
Hello, Vegas.
Nice
I
shirt.
really should have taken the blue pill, to be honest. Yeah.
He went full
There's
Matrix, didn't he? Had the
absolutely
trench coat,
nothing.
everything.
That is
Yeah,
in this
pretty
world.
awesome.
And if it is,
Oh, nice.
we
Lando
really
shirt.
wouldn't like it. And think about those things when you're building your computer system. And actually, I think the example there is actually really good. What I've really learned is that if you really want to build good computer systems, you have to look at the real world. And what I've observed is that the real world is asynchronous. It's not deterministic. There's so many events happening around you, trillions of events, all the time. Yet we seem to function pretty good in an environment that is not so terribly controlled. And so when I think about asynchrony, what I think is that it's similar to that the world always keeps turning. There's, no matter what happens in the world, our planet keeps turning. And so if I think about asynchrony, it is that we should make progress under all circumstances. No matter what happens in our world, in our digital world, we should still be able to make progress under all circumstances. And actually, if I think back about now 16 years when we launched S3, we had a whole series of distributed systems principles where we built S3 against. And one of them is asynchrony. We wanted to make sure that the system would make progress under all circumstances, no matter what the load, no matter what is failing, no matter what new functionality we are introducing in the system, it should always make progress. Now, of course, a lot of it is synchrony because we enjoy synchrony because it seems so much easier. The things we really care about are latency and throughput. And in this particular case, in classic synchrony, as you can see, throughput is 1. And latency, if that one worker has to go through the whole chain of everything that it needs to do and fly one fly by one fly, that was actually pretty amazing. Then you see that latency as well as throughput will suffer. Now, of course, you can add more parallelism to it. You have multiple workers. But they still actually they're probably blocked on a shared resource, which is the fire. And as such, maybe it looks like throughput will improve, but latency will definitely suffer. So getting closer to the real world is asynchrony. You have one or more servers, and they all do is take orders. And then they write this order on a slip and put it on a rail for the chefs to pick up. And you have multiple chefs. Each of them are at a station. And so they all see the order coming by, and if they need to work on it, they pick it up. And you can have these things happen in parallel behind the scenes for you. It is parallelism, but without blocking on any of the shared resources. Now, if you really want to improve latency and throughput, you can have some of these stations introducing actually additional workers. So there's actually this system in the, I think, 90s that Matt Wells developed, which was called event-driven architecture, where basically, you have all the benefits of an event-driven architecture, but you have controlled parallelism in each of those individual units to make sure that they're not blocked with any resource. Again, coming back to the design principles of S3, we took that into account. We really wanted to make sure that there was controlled concurrency and controlled parallelism. Controlled concurrency really means that you have to think about where are the blocking resources that you have in mind. Now, sometimes the world looks synchronous. And one of those examples is bird memorization. They look so beautiful. They are absolutely amazing and mesmerizing. And it looks like there is a centralized controller that tells all these starlings where to go and what to do. Our ancestors actually thought that there was telepathy in the birds that kept them going. But nothing is more true. This is not the thing in the system, because it's nature, and nature is asynchronous. So all the actions that the bird takes are based on local observation. Now, what it does, it has 3, maybe 4 objectives. One of them, it wants to stoke claves to its mates, but it doesn't want to fly into them, and it would like to avoid predators. And so what you see
The whole
there
idea of
is that
opening with
if
this
the
whole
other birds get
parallelization
further
talk is
away,
good, because
you
I think
accelerate.
of all the
If you
things
get
that
too
I've dealt
close
with,
to the other birds,
in
you switch
SaaS
direction.
applications that I've supported, is
And if you are
parallelization
sort
and
of in
async is
a
still
nice
probably one of the
spot
harder
to
areas
make
for
sure that your
developers.
speed
And so,
is like the
thinking
speed
about the
of
master
other
classes
birds
done in the past
around you.
databases
And this
and massive
behavior
data
of
replication at
attraction and
scale,
repulsion
talking about last
looks
year,
like a spring.
I think this is a good talk, actually.
Yeah.
Now, in the 60s, 70s, there was some fundamental thinking, what's called systems thinking. Donatella Meadows is one of those famous authors that's written much of these books about systems thinking. And she already came up with the notion of positive and negative feedback loops. And what you see here with these birds are positive and negative feedback loops. You know? They continuously move back and forth. Actually, in my academic days, I built simulations to do this. Yeah, you have X, Y, and Z axes, and it was basically result to pitch, yaw, and roll. So what you see here is that it's purely driven by local decision making. The bird is completely autonomous, even though the overall system looks like it's working in synchrony, but it's not. This is a pure asynchronous system. So the world works asynchronous. If you look back at those S3 design principles, asynchrony, autonomy, local decision, that we make decisions on local data, simplicity, controlled, asymmetry, symmetry, simplicity, all of those were distributed systems principles, but we derived them from how the real world works. And if you think about synchrony, synchrony is a simplification. It's just something that makes it easier for us to write our programs. But you know what? Synchrony is an illusion. It's something that we've built over a world that is asynchronous. Systems, as we know them, are asynchronous as well. Now let's go to sort of what our digital world, the base of our digital world is, our operating system. Yeah? What does an operating system really do? In essence, it just manages all these devices and adds a number of abstractions on top of it. So how do these devices work? Basically, you have a device driver to make sure that sort of all disks look kind of the same. But what happens is...
This is the part of the talk where I realized that everything I thought I knew about operating systems was wrong.
Don't you hate that when that happens?
System. Yeah, if you want to write something...
I think my entire life, you know.
Share memory buffer, you write something into a register, and maybe you get an interrupt back when the read or the write has completed. And so the underlying processes in an operating system is purely asynchronous. And for a very long time, by the way, the clock is probably the most important device that generates interrupts, because that drives the scheduler and it drives which process gets actually executed. But, you know, for a long time, because everybody thought that asynchronous programming was so hard to do, the operating system had a synchronous interface. If you wanted to write to the disk, you got blocked until actually the block was written. Well, throughput absolutely suffered from that. And latency on the other actions that you wanted to take as well. Now, it wasn't, a number of operating systems in the 90s actually were designed from the ground up to expose asynchrony to the world. Windows NT was probably the first one that had asynchronous communication or interaction with devices as a first principle in their kernel. Linux didn't get any asynchronous though until the early 2000s. And actually all that AIO mechanism didn't really work that well. And it wasn't until, I think, 2019 that we got IOUing in Linux to actually give us truly asynchronous interaction. And why do we want this asynchronous interaction? Because it's natural. Synchrony is just an illusion. And so if you look at your distributed systems and the way that we build our systems, synchrony leads to tightly coupled systems. Now you cannot make any changes to this environment that the shopping cart is involved with without actually changing the shopping cart itself. If anything fails here, probably the overall system will fail. Now, if you look at an asynchronous system, that actually is driven by an event broker, you see that everything is decoupled. There is no tight coupling between any of the components. And so the shopping cart will post an event, the order system will pick it up, or in the payment system will actually pick up the work after that. The most important thing is that this is an architecture that can evolve very easily without having to change any of the other components. Now, if you want to add something like a reporting or an invoicing service, we can do that without changing the overall system. And so why do we want this loosely coupled system? First of all, because they are natural, but they have a number of advantages. There are fewer dependencies. We can actually change the system and change the depending components without that you have to change the others. It is a natural way of isolating failures. If any of these components fails, in what we saw in the previous picture, actually the whole system continues to work. And if the new version of, let's say, the reporting service comes back up, it just replays the events that it missed and executes. So this is what's called an evolvable architecture. That's really what I want you to walk away with. Right? We build systems, but we don't build the end system in one shot. We start off with probably with a smaller system that we can make to work, and then evolve it into the eventual complex system that we had in mind. So the great thing about loosely coupled systems is it's easy to evolve your architecture. Look at S3. In 2006, when we launched it, it consisted of 8 separate microservices. Now, it is well over 235 different microservices that we could add to the system without taking the system down, without any impact on the other pieces. We had new storage methodologies. We added new policy mechanisms. We added different storage tiers. All of that while the system was running and could evolve. So evolvability is extremely important when you think about designing your system. Again, we knew what we were doing in 2006. Decomposing into small, well-understood building blocks is the fundamental part of building these asynchronous, loosely coupled, event-driven systems. And actually in Amazon, we went through, Amazon the retailer, we went through similar kind of history. We started off with a monolith. And when that had reached the end of life, because we couldn't scale anymore, we couldn't evolve the system. Because it was all driven by sort of shared resources in the back end, a whole battery of databases that were direct access. And so when we wanted to actually start innovate more, we couldn't do that because we couldn't evolve the system. So we moved over to service-oriented architecture with coarse-grained services. We learned from that. We went to a microservices architecture. And now Amazon Retailer is basically a very large collection of microservices running over a shared infrastructure. Actually, about a week or 2 weeks ago, I published this document. This is out in 1998. It's called the Distributed Computing Manifesto. And it's actually how our engineers were thinking at the end of the 90s about how to deal with the fact that they couldn't evolve their architecture. And how that moved over to a service-oriented architecture. This was way before anybody knew what a service-oriented architecture was. Engineers in those days at Amazon, and still are absolutely amazing on the front end of engineering and basically invent their way into the future. I urge you to read this document. It's dated, I know. But for many of you, you'll recognize what's in that document because reality, for many of you, still now that have to work with monoliths. And next to service orientation there,
Too
there's a
true.
big chunk that says, and some of our work is workflow oriented.
It didn't feel that dated when I read it
It's an amazing document.
a few days ago when they published it.
Just for fun to see how engineers almost 25 years ago were thinking about it. Now, the workflows are important. It enables us to build these applications from loosely coupled components. How can you compose them? How can you bring them together? How can you evolve it? Yeah? And so, to be able to build workflows, you need to have these patterns. You need to execute things in sequence, or how to do retry handling, error handling, routing based on data, all these kind of things. And in AWS, we have 2 services that basically provide these basic concepts for you. And you already know them. It's step functions on one end that handles all the different types of executions, and AWS Event Bridge that sits as the spider in the web as being the event broker. And one of the patterns here is really that you should be using serverless components to combine, to stitch together, to get the overall system that you want.
I've seen one implemented or the others, but I've never seen both
building these
Well,
workflows.
I think that's what he's saying, is that they both sort of handle workflow.
Start doing things that you never expected them to do. Yeah? And so for us, it's always really important to learn.
Typically, I don't think you'd use
to learn from it and then try to improve ourselves.
both, unless you have one triggering the other for specifics.
For example, there was a particular pattern that we hadn't anticipated when we were building step functions. And it's that customers actually would like to do map reduce with step functions. I go like, what? Yeah, after all, we have Kafka and we have EMR. The customer said, no. We want something way more simpler. I just want to write 2 Lambda functions, and that's it. And so one of these examples is, for example, so NOAA publishes the measurements of weather data stations around the world, and then puts that on a daily basis in a public data set. And the data set is about 37 gigabytes, and it goes spread out over 500,000 files. Now, imagine you would just want, from all those files, you just want to get the station with the average high temperature at that particular moment. It's a very simple operation. And so to do this, they just wanted to write 2 simple functions, 2 simple Lambda functions to do this. So I'm happy to announce today that we're now giving fundamental support to this pattern using AWS step functions distributed map. So basically, I didn't build it. Go talk to the guys that actually built this stuff and give them the applause.
Nice.
Because listening to our customers is really important. So what we can do with these step functions, and actually in the distributed map, is basically do a map and a reduce step very easily. So it starts off with using the step functions distributed map, which then will fire up maybe 1,000 of instances of your Lambda functions to process the data and then summarize that data in a final Lambda step. This allows you very easily to process very large amount of data using very simple Lambda functions. Now,
I'm trying to figure out, like with parallel, once they released parallel executions, I was sort of doing the same thing. So I'm like, I'm trying to, what's the announcement here?
nothing we can do about
The
it.
problem was it was very static.
No matter
you
how
could,
much
you could
you
fan out
want it to be not
to
a scale,
X many functions,
and how
but it
you
was always that
want
many
it to
functions.
be
You couldn't
all
dynamically take
determined.
some data and say, okay, this time I want 1,000 or this time I want 500.
So the
It
best
was,
way to handle that
It was hard coded into the flow, but now we can fan out sort of arbitrarily and back again.
Got it. Okay.
And the event-driven architecture leads automatically to loosely coupled systems. Now, what are the sort of the components, the patterns in there in an event-driven architecture? You have the events, you have event producers, event records that get distributed, and then you have an event broker that decides where these events should go to. These are just the basic components of an event-driven architecture. And if you look about sort of the communication patterns in there, it's either point-to-point, which can be a queue in the middle, or event bridge, or a publish-subscribe, which event bridge also supports, and then a streaming pattern, which is actually really interesting, because it means that any of those consumers, CD or E, can actually fail, come back, and replay the events that they have missed. All of these are very important patterns, and actually Event Bridge supports all of them. If you look at one of these sort of simple kind of architectures of an event-driven system, you have API gateway, you have 3 different APIs there, create an account, create an order, list the orders. Probably create account does a really simple thing of, let's say, create order, store something in DynamoDB, post an event to the event broker, and then the order service and the shipping service basically go off and do their work. And actually a really good example of that is something that Martin Fowler gave. And you must all know Martin Fowler. If not, look him up. He's one of the most famous architects in our world. And he's really a big proponent of event-driven architecture. And this example that he normally gives shows that, services can be end consumers and producers of events. You have a shopping cart, request an order, the payment service probably does an authorization against your credit card, gives an OK, order service picks it up, posts more event, shipping service picks it up, and shipping events happen, it actually pushes it out again. It communicates basically with itself through the event bus. And then it goes back to the order service in the end. Now, this is great. Now, all these components are loosely coupled, fail independently, and most importantly, the whole system can evolve very easily. If I want to add an email notification service, it's easy. You just plug it into the event bus. If you want to add an invoicing service, for example, you can have a little process sitting there that picks up the event, put it on a queue, and then maybe you have some commercial software running in an EC2 instance that then picks up the work from that queue to create invoices. It's all very, you can easily involve it. Actually, I make a little sidestep here because I recently saw an event-driven architecture that I was amazed by how simple it was, and how important it is at the same time.
I mean, this is every app these days, right? Like moving
every app looks like this.
To this.
Failure with readme.com.
Readme.io?
Now, there you post descriptions of your APIs just that others can use them. But if you change your API, you need to remember to also change the description. Now, you can actually automate that. If you change the API in API Gateway, it generates an event that goes to CloudTrail. CloudTrail then posts an event to EventBridge. This triggers a Lambda function. This Lambda function picks up sort of the configuration information from AWS System Manager, and it gets the secret API keys from the AWS Secret Manager, and then posts the updates that you've just posted to API Gateway on readme.com. This is a very simple thing. It's actually on, it's on one of the blogs with example data, example code for SAM. You can immediately start using this. And I know this seems like simple, but it's an important part of the way how we evolve our systems. If you evolve your API, immediately the documentation gets updated. Now, again, it's event-driven architecture. You want to add
that simplicity is the beauty, right? Like, because everyone talks about operational toil and how much work, they have and these types of things. And putting something like this in place may seem like it's got very little return because it is just updating your API description. And
all complex systems.
But over time, the amount of times that you do that, you saved a ton of time.
Simpler systems.
That's true.
And haven't had a missed manual handoff.
Asynchronous systems are so close to the natural world is that you can actually make complex systems work. Because remember, this here is a pretty complex system. We're able to make it work because we have independent actions to be taken without total control. And it's actually not just the architecture. Now, if you remember the Amazon two-pizza team approach, is actually built on this. It allows you to have teams to be focused on one particular component and one particular component only. They don't need to know the big picture. The ordering service doesn't need to know that there is an email notification service present. So you can evolve the overall system and move really fast by focusing on building your local components. Really. It is really evolve or die. Because if you want to really build your complete system from scratch on day one, that's probably not going to be a simple system that works. Build
Need that on a t-shirt.
And evolve. And the best way to make evolvable system is to focus on event-driven architecture. If you've been in the expo hall, you probably have seen the serverless espresso scan. Now what you can do with serverless espresso, the serverless architecture behind it, you place your order on a mobile device, order appears on the monitor, you get a notification when your drink is ready. This is how the architecture looks behind it. It uses step functions, it uses event breaks, it uses a whole execution pattern over there. You see how this easily works.
That's kind of awesome.
Maybe it looks a bit too complex for just an ordering application. But the cool thing about this is that it's easy to evolve. If you've used the app, you know that there is a mechanism for there where you can actually see the journey that each of the steps of the architecture are going through. And the developers could just add this without changing anything in the overall system. Now I know, sometimes synchronous systems, because it's a convenience, they look so much simpler. And asynchronous systems, you have all these components and event bursts, how they work together, can sometimes look a little daunting. And so I've been thinking about how can we simplify this? How can we make it easier for example, developers that never used serverless before? How do they know where to start? Which services do they need? How
What magical unicorn is he going to announce now?
I really wanted to make this easy.
Please be something cool.
Yeah. Well, I mean, the problem he's talking about is really hard.
It is really hard.
Composer, which simplifies and accelerates the architecting, the configuring.
It's a no-code solution. Visually design and build serverless apps. I don't know if that's exactly what it is. That's what it sounds like.
It looks like that's what it is.
It has a...
Visually... Yeah, that's what it is.
So is Honeycode dead?
You can connect these resources together to create a serverless application architecture.
Well, this is what Honeycode should have been
sort of the common
to begin with.
Generating either SAM or...
It's just a very light abstraction on their existing services instead of its own.
You build these sort of different components together in your canvas. One click of a button, you've got a CloudFormation file or a SAM file. And of course, it can interact with your local disk. So you can store all the files in your local disk, so you can either continue to work in the canvas, or you can just use your usual IDE to start continue to build your application. And so it's also, of course, because you now have a visual model of your service application, it's really easy to share this with your colleagues.
See, what I want is the other way around.
Right.
Just better take a SAM app and turn it into a picture.
From this environment, from the application composer as well, onto AWS. And it makes development so much faster. If you can just
does it?
Those for you. You don't have that much experience with serverless applications.
Like all these Lambda boxes you got on the screen, like that they've just written themselves? Like, I don't think so.
Make it easy for you to get started with building this application. Now, another concept for nature.
But I wonder if that's just, when I think about my journey into cloud, like, am I to the point where that doesn't help me, but someone who's, who's dealing with a monolith day to day or simple 3-tier web app? Is this really the, what they need to get kickstarted into event architecture? So it'd be awesome.
And it was scheduling. And EventBridge is one of the fastest evolving services that we had. This year, for example, they added schemas, they added event archiving, and they added the EventBridge schedule, which is amazing. You can basically have either cron-like functionality all the way over to actually scheduling millions of events. And so EventBridge is an extremely powerful spider in the web.
So with EventBridge and the new low-code Lambda thing, it makes sense to me how those all tie together, because now you can take input from any system and then transform it through this connector to basically it gives you kind of like a really simple ETL pipeline almost to different Amazon services, which could be really there's complicated apps which I think can help with that too, but like this is just really nice for just integration perspective. It's sort of like, instead of having to write code for all the Lambda spackle we write all the time, you get a little bit of a low-code option to then dive into the spackle, and the heavy-duty coding when you need to. It's not a bad play, actually.
Well, but it's more the execution of the Lambda speckle, isn't it? Like, it's not writing the Lambda functions
I mean,
and the logic
it doesn't write
inside
the function
to do the
necessarily,
ETL.
but with EventBridge, you're getting a lot of that stuff you were writing as Lambda spackle out of the box.
That's true.
So
The
you're
rules and
writing less
filtering,
Lambda
yeah.
code, and then you're giving it a workflow engine around it, so you can move the data between systems that you want to. So yeah, you still have Lambda to write, but it's just less Lambda to write.
Yeah.
So in Unix, the composability happens because these small components.
I mean, if you could
all
focus on just business logic and lambdas
and use text.
compose it, plumbing it all together.
Not parsing the actual event body. Yeah.
This is just a joking.
Which, is most of the, logic you write in those
Imagine you
things.
have an access log. You want to filter out the IDs of customers that experienced an error. So you get the API lines from the access log. You look for the 500 errors. You reverse that. For some reason, the customer IDs from the back.
This is fantastic. It's bringing it down to, like, sysadmin school. Like, I've written this.
And they can sort a unique.
I have this in my code repo.
So basically what you get is you get a list of your customers that experienced this error, sorted, and with only unique, no duplicates in it. Easy to do. And you can build many, many, many different applications using these very simple components.
Yeah.
Now,
So you have 1,000 servers to run it on.
What is it? 40 years later? 50 years later? That this was such a powerful
I'm
concept.
always impressed how much sweat he sweats.
Not a Christian.
It is really fantastic.
Give AWS
Like,
service.
he looks a little smaller. I don't know if it's
However,
I just
No fitting teeth?
he's looking a little bigger.
Thompson originally had it easy.
Oh,
And
yeah.
Thompson actually, after
The
the
pandemic
90s,
wasn't good to
figured
me.
out
I
that they
can't
wanted
imagine it was good to
find-
him.
rewrote
Yeah.
all the applications that they had. Well, that's not as easy to do in AWS. Yeah? We have no uniform way to compose events. And it's also an all or nothing approach. If I connect to Kinesis, I get all the events. Yeah, or to DynamoDB Stream. And so many of our customers, they want to actually build these sort of connections between different services, have to write a lot of glue codes. And as always, I kept thinking, why can't we just use the pipes principle here? So, happy to announce today, Amazon EventBridge pipes, which allow you...
Yes.
That's cool.
That's very cool.
Which allow you easily to stitch AWS services together.
Does it support copy?
Yeah? And it's a new feature specifically designed for
It
integrating...
might support
It might.
MSV
AWS.
or
MSK,
MSK.
Yeah, and so it is a point-to-point.
Well, you got the wrong acronym on
Event
too, because I always have to think really
against
hard about it.
consumers,
What's the magic
and
concept?
it's able to manipulate the event.
A little early.
Yeah, so the idea is that you should be able to no longer have to write the glue code. You can easily stitch these services together. And if you would want to actually manipulate the events before they reach the consumer, you can actually either provide a Lambda function or a point to step functions or API gateway to actually run some code to manipulate the events that are flowing through your pipe. And it has built-in
I thought you could do that in EventBridge
meaning that
natively.
if
I
you
guess not.
only want to get a real subset of the events that needs to flow to the consumer, you can add that too. So basically, this is pipes on steroids. Because it's not just easily composable, it's actually also an ability to manipulate the events that are flowing through your pipe. This will definitely reduce significant costs for quite a few of our customers that have been building these kind of systems of stitching AWS services together and no longer have to do that because now we have Amazon EventBridge pipes.
Yeah, the amount of
Think
kludge
about
code
the
I've written to
Let me take a
trigger on ECS scaling events.
I
All of that is now gone.
wanted to go to a
Even
football.
like doing like S3 events.
In this
even,
case,
they gave us a
Arsenal
really powerful
and
ability to take
Liverpool.
an event object coming out of an object
Arsenal!
manipulation, and then you had to write into Lambda
Don't do it
code or
red.
step functions. This can also
Okay.
be
To parse
programmed
that event,
for that
yeah.
too.
It absolutely could.
No,
Yeah.
I'm not an Arsenal. Yeah, I'm a bit of an Arsenal fan because they just look like Ajax. Yeah, play beautiful football.
It's no
but-
code without saying no code.
Hey, if you don't call it no code, then I don't mind it as much.
Yeah.
I only here. Okay, so but you need
I
to
really
be an
get
Arsenal
wrapped around the axle when they call
Why
it
you think-
bespoke
for the game.
coding.
And so I went to
The actual, like, for what we call normal development engineering, that's when I'm like, ugh.
I've never used them before. So I wanted to figure out whether
it's like branding, man. I don't like that. Yeah.
Mm-hmm. And I actually used
bespoke developer. Like, go after yourself.
What's mine?
Yeah.
I went to
How many bespoke tailors are still existing in the world? Like,
don't
put that dead word on me.
Of those ticket broker, and I actually bought the ticket. I later learned that Trustpilot.
I do sort of miss the Andy keynote where he would poke at Oracle.
Very interesting.
That was always fun.
And I would like.
I always thought it was punching down from Amazon.
To give you some real world.
I mean, is it punching down when you're punching at a company that makes?
I mean, I don't care because it's Oracle. But
yeah.
Director of Engineering at Trustpilot.
Thank you. I love the energy in this room.
Trustpilot.
I'm here today
know them,
to talk about a single word. It can be hard-earned, but has the power to shape our relationships and fuel business growth by increasing consumers' confidence. That word is
trust. Yeah. It's in your name.
At Trustpilot, we enable people to read and write reviews and find companies they can trust. Because reviews help people like you and me to have more confidence in what we buy.
I was going to make a joke about her pacing, but then I realized that she's doing this in her second language and probably doing a better job than I would be able to do on stage.
I mean, on a comment on diversity of on-stage and main stage this year has been fantastic. Like, I think last year we commented how white all of the people were and male, and this year we've had a good mix in general.
We help ignite trust within this community, and we are on a mission to become the most recognized symbol of trust on the internet.
I just had to look you up. I'm not really feeling that.
In 2007, we've grown to house over 190 million reviews. However, our growth hasn't been linear. In 2021 alone, we have received over 47 million reviews. And the number of reviews is constantly increasing, while their importance is becoming more critical. With the large volume of reviews, our service must be trustworthy for us to succeed. And to scale trust, we need to have both reliability and integrity. However, scaling trust is no mean feat. Today, we are in a strong position, but our journey hasn't been without effort. If we look at where we started, our platform was built on a monolith and on-prem databases. Our experience started well, but we soon found we were unable to handle our growth. Hiring more people.
I gladly decided not to live tweet today.
This
is too much.
And reverting bugs were all ahead of us. And more usage caused more reliability issues.
So they use SQL Server.
Product outages. Not the best experience for our users. Now, I still remember Trustpilot's Christmas parties in the early days, where all of us developers were prepared to go back and work. Because it became a tradition for some outage to happen during this event. And of course, what better way to stabilize our platform than after a few cocktails? We knew we needed to make a change. So, we transitioned to an event-driven architecture. So how does that work?
Slowly, apparently.
Are obviously at the core of our business. But now, let's look at one. Meet Sylvia, who had a great experience with a flower shop and wants to share it by writing a review on Trustpilot. When Sylvia submits her review, behind the scenes, an event is being published to an Amazon SNS topic. The review submitted topic has over 20 subscribers, with each one of them completing a different asynchronous process using Amazon Lambda, Amazon ECS, and other Amazon services. One of those processes is to publish the review, which is another Amazon SNS that fans out for Amazon SQS to consume and trigger other processes. One of them being storing the data. Now, choosing the right data store has been a challenge in itself, as the number of reviews being read daily increased from thousands to millions.
Christmas party outage. One of the top 5 worst times for outages. I love you.
Cost-effective database. And Amazon DynamoDB stood out as the right candidate. We all know we can plan for expected increases in traffic for events such as Black Friday and Cyber Monday, which just passed, even when having a monolith architecture. But our latest event-driven architecture and the use of Amazon DynamoDB provides us with increased
Trustpilot, customer reviews of
meaning
things. Like a Yelp.
both expected
Another
and
It must be big internationally, because
traffic increases can be
like, I just
You've never heard
I've
of it
never
before?
heard of it, but yeah, looking online, it's a little strange though, because it's like Yelp, but you would sign your business up for this, so it's and then advertise that you can put reviews on Trustpilot. I'm very confused.
all
I decided I was missing the point and
as a
should probably pay attention to the
reviewing on Trustpilot became more important than ever. This increased our traffic more than we could have ever predicted. But thanks to the cloud elasticity and the use of an event-driven architecture, our platform is able to scale for expected and unexpected traffic increases, while our teams can continue focusing on
I'm
product.
going to start doing all my my bar graphs with red backgrounds and green backgrounds.
I also made a mental note to completely steal that and the smiley faces.
Yeah, no, I liked it. And,
On
yeah.
Trustpilot is one challenge, but maintaining authentic, useful, and trustworthy information
This is pretty good too.
is quite another. If we go back to Sylvia's review, by treating everything as an event, we are in a position to easily integrate and evolve our existing architecture.
It's a big deal.
As an
Like,
example,
getting into an event, you know, so many applications are just event-driven, and then to actually be able to decompose it into an actual event pipeline is just fantastic. And it's so easy to change.
To our
It's
They're
just-
already in the monolith. They're event driven, right?
yeah,
Moving
you
from
just do
library to
handoffs in the
library.
monolith. Yep.
Yeah, and it's so funny how hard it is to teach people this concept of like, no, spread that out across these multiple things. Your life will be better for it.
have functions,
And they do struggle a little bit with the latency hit they take, because you know, especially if they're separate microservices components, but that can be managed if you're aware of it. But
just to
Well, then, yeah, I mean, and that's, you know, you want to have asynchronous. You want to have these things be
having an architecture
not
that can
require parallelism in order to process,
is exactly
because
what we need.
that's where you take that latency hit. Is this has to work before this works.
Our platform, as well as increase team productivity. But what about the future? We live in uncertain and rapidly
I think
changing
a bad pattern is trying to build a synchronous system
all
using
these
asynchronous
and vice
components. I see people fall into that trap all the time.
makes Trustpilot
Yeah,
more
I've built that.
make
Have we all?
better and more trusted decisions about who and what they buy. We won't stop here. We will invest to bring more features to health, and with that, I want to say thank you, AWS, for helping us create a more trusted world.
Very nice.
Thank you, everyone, for listening.
I'm going to take bets. Somebody's going to end the keynote today with another story about
I forgot to
cancer.
mention earlier,
No.
Angela is part of our AWS Heroes program.
Ending on cancer? That would be
AWS
rough.
Heroes program.
Including another thing on cancer?
253 AWS.
I mean, AWS Heroes are not cancer, so.
53 countries
Yeah.
whose enthusiasm
Yeah,
for
but this
knowledge
is like,
sharing
you know,
and
the
making
middle.
the community better is unparalleled. They have a real impact on the community. I'd like to thank every one of the heroes here today for all the effort that they put in to actually make all of us better. Thank you. Go on over there.
Shout out to the heroes.
It is one of these things at our AWS event. Now, we give, hundreds, if not thousands of classes to you where you can learn. But the best way to learn sometimes is from the people that sit next to you. Because you really hear sort of the struggles or the obstacles or, this pattern worked really well for us in this particular situation. Sometimes stories...
That's not what you learned. You learned the other way. This didn't work at all.
So really, I always urge you, everyone in the room, to talk to each other, to learn from each other. Because that's absolutely the best source of information that you can get. Now, one particular architecture that I think has become more prevalent is to think about how we can run our architectures at global scale. We now have 30 regions around the world.
Because they announced 3 before reInvent, 1 a week.
As close to your customers as that you can get. But how do you do that? So what is an easy way, the most convenient way to actually build those type of architectures that need to operate at global scale? I believe, and I'm strongly believing in that event-driven architectures are the ones that you should use to build applications that need to work at global scale. And we've been doing that ourselves for quite some time already. And let's dive into how one of these global systems actually work for Amazon, for AWS. So DynamoDB is, in my eyes, one of the powerhouses of databases. It routinely does trillions and trillions of requests a day while maintaining single-digit latency and is able to operate at global scale.
At least 1 trillion of those 10 is me doing full table scans, trying to figure out what data I have.
Of DynamoDB. And in this case, I only want to actually look at one particular feature, that is how our global tables actually implemented. Because I think we can all learn from that if we build our own applications that need to operate at global scale. So global tables, it gives you the ability to just write to your local DynamoDB instance, and it will automatically replicate those updates to other regions that you've indicated where you need to have global tables available. And it gives you a multi-region, multi-active database. You still do local reads very quickly and fast, while actually having the tables globally available. And so what's underneath there is what they call an active-active architecture, meaning that you can write to any of the instances of DynamoDB in any of these different regions, and updates are automatically propagated to the other instances. There is no synchrony here. It's a purely asynchronous environment. By the way, the alternative would be that you would have sort of a controller, and actually once that subscribes to it, that is not a very reliable architecture. Because how would you build this? Would you really use sort of synchrony in that? Maybe if you would want to. But if you want to have a really highly available system that can operate at global scale, where interruptions happens all the time. Yeah? If you need to run some form of two-phase commit over the instances, then it's most likely that a significant number of your transactions will fail. Now, we should build it then using an asynchronous approach. And so we, just like anybody else in this room, can make use of a number of features that DynamoDB has to offer. One of them is DynamoDB Streams. So we built a replication feature on top of a feature that DynamoDB already offers. Basically, the replication service reads from the DynamoDB streams for the updates and then propagates them to the other regions where it needs to. So the other regions also have a replication service. If you get writes in Europe, it will automatically propagate to America as well. So what sits in this replication service is basically a whole collection of replicators, thousands of them, because you may actually replicate many different...
learning as fast as I can, because this is a really hard problem that you have to solve.
No, it's a super hard problem.
For this event-driven architecture.
Intrigued by it.
If any of the replicators fails, it easily gets restarted again and can reread from the queue to pick up exactly where the failed replicator had stopped. And so we can have thousands of these replicators. And so they take care of replication to any of these other environments. It's a purely event-driven architecture. Mm-hmm. Now, if you think about the patterns that we see here in event-driven architectures that make this work, you need to have a change data capture facility, being able to see what were the changes in the data that you would need to propagate to other regions. You need to make this asynchronous. Right?
See, the first two parts people do really well. The last part, self-healing replicators, not so much.
That's the part.
Asynchronous will give you failure.
That's a ticket to the SRE team.
It will give you
exactly.
evolve the system very quickly. And it will actually deal with replication. So self-healing replicators here using the queue is something that makes it very easy for you to build these systems in a highly fault-tolerant way. Mm-hmm. Now, of course, we see many of these patterns. Now, after all, the world is built out of patterns. You see them everywhere in nature. So we should follow these patterns. And of course, us as computer scientists, we have all read the book on design patterns from the famous Gang of Four. At Amazon, though, we keep our patterns in the Builders Library. And I once again urge you to take a look at the articles in the Builders Library, because they are the collection of knowledge of Amazon engineers that have been building highly reliable, scalable global systems over the years. And so the two new articles that I would like to point you to, one by Claire Ligori, and it's my CI/CD pipeline is my release captain. And the second one is by David Janichuk, and it's called Using Dependency Isolation.
CI/CD pipeline is my release captain.
Brilliant article.
Might be good.
Yeah. I mean, the previous article by Claire for CI/CD was really awesome as well.
It was really great, yeah.
Quite a few of the articles also deal with, what I would say, the heavy lifting around development. About having to set up your environment, having to maintain your environment. How do you do rollbacks? How do you integrate your CI/CD pipeline into your system? All the things that are basically, in my eyes, sort of the heavy lifting of development that have nothing to do with
forgot about the library.
And so, imagine
I use it all the time still.
Or, everything slows down if you have to deal with different types of tools that sit in.
Yeah, I read a lot of the articles when they first
So we were really thinking about,
I was not checking
as
it regularly.
always, how can we remove this heavy lifting for you?
Future
I'd like to announce today Amazon Code Catalyst that takes away all the
fairness and multi-tenant systems
that sits around development.
Looking at it on the website right now, and I'll be doing some reading tonight.
Software development. What?
We've built this with developers, teams, and cloud in mind. It really helps you to sort of plan and develop and collaborate and deliver applications from AWS. It has all the tools you need to go from idea to production much faster.
Is this a replacement for Elastic Beanstalk?
Right here, for example, a single-page application. That's what you
Oh,
do.
it's like
And you will get all the help you need to actually set all of this up.
it's like
You can actually add
Light
also
Sail?
your own
No,
group,
not Light Sail.
or
What's the
the organization can have
the
a specific
IBM Red Hat
that they want you to
container
follow
thing?
in the way
The
to
service
develop
catalog
applications.
for containers.
And
OpenShift?
Blueprint
Yeah,
not just
it sort of looks like
creates code.
OpenShift-y thing. Like here,
Uh,
here's a you
it
want a
does
single page web
everything
app,
else.
and we'll
It
give
sets
you this
up
thing, and we'll give you a
project
repo,
files,
we'll give you all
it
the
configures
parts.
integrated tools, source control, CI/CD, issue management, and the service allows you to actually swap in popular tools like GitHub. And so, a important part, of course, in all of this is how you can easily set up the CI/CD pipelines, or you don't have to set it up; the system will set this up for you. Yeah, and you
That's
can
nice.
define build
That's
actions.
cool.
Sweet. I think I am finally out of a job. That's fantastic.
And it's a very easy way to deploy on AWS, across services, across regions, across accounts, in a global manner. Yeah, and it has built-in support for code coverage,
cool.
unit testing, automation,
very cool.
report generation, all of that stuff that I consider the heavy lifting of development that actually doesn't help us to build applications faster. It will hopefully take away all that heavy lifting for you now. One of the problems I always see is that engineers, developers, builders need to actually work with many different code bases. Yeah, you may have one version that actually needs to run against Python 2.7 versus 3.9. They're not compatible. And actually being able to switch to two environments, building the same application using these two environments is pretty hard. Code Catalyst makes this very easy for you to switch between these environments without that you have to do any of the heavy lifting required for that. And so, you can auto-populate your project with code and dependencies, and you can use your favorite IDE like Cloud9 or
The news
VS
blog
Code,
post has not been
JetBrains.
dropped yet. Come on, Jeff.
You can replicate and share your development environments really simply. Actually, inviting people to join your project is the only thing you need to do is fill in an email address, and immediately that particular teammate has now access to all the code, to all the issues, and to all the deployment reports. We realize, of course,
So it's outside of Amazon authentication?
More than just the AWS server.
No, it's got to be integrated with single sign-on, right?
You just said all you need is an email address to share the code.
So we've
Well, an
expanded
email address that's tied into a single sign-on system.
Jira,
Yeah, I don't know.
But no Teams?
of course, the
Come on.
popular IDEs like Cloud9 or VS Code and JetBrains, and GitHub is of course integrated into all of this, because those are the services we all use right now.
What's
and
Mend?
Code Catalyst
Look it up.
integrates that into your environment by default. And indeed, it's all about moving fast, so that you can focus really on building the code and not spend too much time on all the issues around it.
Oh, White Source
So,
changed its name.
Thinking about Inventive
They
Life,
did?
one of the things
Yeah,
that
White
it
Source is now
evolves
Mend.
easier, it evolves much faster.
I didn't actually have to, isn't...
And so, for example, I met recently a company in the UK called Cinch. They're an example of a company that makes use of 3D technology
Why don't they
to
change
show
the
you
name?
cars. And so you can basically be at home, look at this car, decide whether you want to buy it or not. And actually, they built this in 6 months. And so there's
I'm actually so surprised that really nothing came out on main stage for anything around code security, code,
and then
Yeah, supply chain, anything.
Yeah, I was surprised. I thought there'd be something.
Open search. And then all these components can publish events and retrieve them, and it's an easily extendable environment for them. One thing, actually, that's very
Well, we're failing as a podcast. Mend. White Source changed their name to Mend in May of this year.
They actually had all of their
I don't think that is too much of a failure. Yeah.
Every car is
idea.
captured in 360 degrees, and with the interface on their website, you can just look around.
Again, going back to the Amazon Builders Library. Colin McCarthy has reliability, constant work, and a good cup of coffee. That's going to be
Really arising in our
Yep.
digital world.
Add that to the list.
But the
Yeah.
world,
That guy's smart.
after all,
making retries safe with idempotent APIs. That's
not just one line.
too.
That's awesome.
It's not just
Yeah. Oh, yeah. No,
Why?
I'm gonna
Because the machine
assign this to people.
keyboard,
Make it
screen,
required reading.
mouse, finger. That's how we have built our digital systems and how we interact with them. But it's not the real world. The
I don't
real
know how long this
world
one's been around. Automating safe, hands-off deployments for
How
the
can we
player.
get our digital
That's the one that I read
That's
from
the
the
one,
time.
yeah.
It's been around a while.
And we already seen great,
I was
great
like, is that the one I read or
strides in
not?
that. You know, Alexa and other voice systems.
The fairness of multi-tenant is going to be good too.
Without
Yeah.
knowing that they're digital systems.
Because that's a very hard challenge, right?
That we
That
all
as
use.
we're
This is not a
building
Slack
more and more
channel
multi-tenant
where we
systems.
sharing things.
Using
This
dependency or
really
isolation to
is
contain concurrency overload.
Yeah,
Wow,
and
that's
so it's
not my
normal.
problem right now.
Normal
It's
way of interacting
probably
with
good
each other.
geeky too.
And as such, we should use normal technologies to
It'll be in the next set of problems after we fix the initial problems, right?
Soul Machines
Yep.
is a company that have actually taken this a step further. They actually have digital personalities that can express emotion while you're interacting with them, which is another very normal, natural kind of way of interacting. It's not sufficient to hear what I say. You're all looking at my face. What do I think is important? What do I not like? Liverpool, for example. And so Alexa and Soul Machines are already the first steps in this. And our real world is multidimensional. And as such, we should be looking in our digital systems to present the world as multidimensional. Again, I had a really great experience recently. I was giving a birthday present to have a new pair of shoes made. Now, my feet are ugly. And so I was amazed that I now would have shoes that would exactly fit my feet. So we went to this store of James Taylor and Son. And they were cobbler out of 1857. And they used the same techniques and processes today as they used 100 years ago. They produce what is called a last, which is a physical representation of my shoe in wood, against which the shoe is being made. And I was really surprised, actually, that this 165-year-old company actually was using very modern technology to get this done. I get to sit on a chair and put my feet on a device that had a bunch of cameras that actually made a 3D image of my foot. And then they were using that 3D image about then to make the last out of that and make a pair of shoes that exactly fit me. And it seriously made me think how 3D technology has permeated our world already.
Is that foot missing some toes?
It's really great to see actually also.
I'm hoping that's like a foot with a sock.
Yeah.
This business is innovating and using digital technologies like 3D to actually improve their products. And they're not the only ones.
And if
remember,
it is, he's
this
got a
is
lot
what
of socks with holes right at the big toe. That's
Jeff Bezos once described our
Stress
customers as divinely discontent, meaning their expectations are never static, they only go up. And this is true, especially in the shopping patterns that we see. Yeah? Just a few years ago, if you wanted to buy a pair of shoes or some furniture for your house, you had to look at static pictures. You had no idea how this would fit on your feet or how it would.
The real world is multidimensional, the real world is not a Slack channel. I just said that.
They would order 4 variations of the same shoe.
Is he going to go with augmented reality here in a sec?
Try them on.
If he goes in the metaverse, I'm out.
And send the other thing back. I had a very bad customer experience.
I do like the option to see this item in the room on the
what can we do
Amazon.
better there? We need to make sure
Great
that
sales
the way that our
tactic.
customers can interact with us is like in the real world. I need to have 3D images on a 2D screen
The
to make
user
sure that
does
we
that
can have.
for
Now,
Catalyst.
fortunately, browsers have started to introduce things like WebGL that make it easy for you to have 3D images to be displayed anywhere. It needs a lot of math, though, actually, to create these images. Now, what you can see here is something that we've built in Amazon called Virtual Try-On. Basically using augmented reality to see how the shoes would look on your feet or how it would look like with other clothes that you have.
The things that are in the Amazon store that you can do this with is sort of odd. some of the things make no sense
Instead
whatsoever.
of having to order a lot of them and then send many back. what is called virtual trial. Now, 3D models are worth 1,000 pictures. Actually, about 130,000 pictures. You would want to make a 3D model using 2D imagery, and you would go over 1 degree over each of the axes, over the x and the y axis, you actually end up with 130,000 pictures. And actually, if you add the third axis to it, you would get to millions of images that you require. Now, it's used over all industries, and we really want to make sure that this becomes much easier. You can't take 130,000 images to create just one 3D image. You have to get close as possible. Now, it was once necessary to have these sort of complex CAD 3D drawings to then create a 3D image out of it. But there's a technology, actually, that is already 100 years old. It's called photogrammetry. And it's the science of how many images do you really need, 2D images, to create a very good approximation of a 3D world. And so many of our customers already have these kind of pipelines, where they take a whole set of images and then make use of, for example, machine learning to stitch them together, and then in the event-driven architecture, of course, and then stitch them together to create the many different object forms that there are. There is no PDF for 3D. There's about 6, 7 different popular object models that you need to create out of all of these pipelines. Quite a few of our customers have thousands of products, and so they really pump these things through this pipeline. Now, there's a lot of research happening in this world. There's something called NRF, which is neural radiance fields. And this is the science that how many images do you need, and then use machine learning to actually fill in the gaps. Actually, it's a bit like how we as humans work. We all think we have brilliant peripheral vision. Not true. Actually, we don't really see that well in peripherals. It's our brains, however, that stitch these things together and fill in the gaps. That's what NRF is as well. Now, how can we make use of machine learning to fill in these gaps? You can actually only need about 12 images of a 3D object, if it's not too complex, using NRF to create a 3D model. And given that this is becoming so prevalent, I honestly think that 3D will be soon as prevalent, as pervasive as that video is now.
Well, how are the movies?
5, 6 years ago, video was still much more...
Even if there is an Avatar sequel coming.
These days, everyone's putting it everywhere. 3D will be the same. And they are, of course, much more useful than 2D images because they're close to what the natural world gives us. And also how these objects interact with the real world. And remember the augmented reality for these shoes. But what if you buy this lamp? Now you can put it in your living room. How does it look like? By the way, not just how it looks like, imagine you switch it on. What effect does it have on your room? What if you move this lamp to the other side of the table? All of these things you can do actually by now in a product called View Your Room, but it's something that actually will become way more prevalent soon in all sorts of other settings. This, of course, means that you not only need to create a 3D object of the object that you're interested in, but you also need to have an accurate representation of the environment where it is in. And so we already have a number of engines that work really well in that, Unreal, Unity. And actually, we've been investing significantly in a open 3D engine, OpenThreeDE, which is maintained by the Linux Foundation, which gives you the environment to actually present you a 3D environment for you. And actually part of that is also Epic Games, who control who control Unreal. Yeah, they're also participating in this. We want to make sure that there is a 3D engine available for you that works really well in the cloud. Now there's also partners that actually work in this space. One of those is Matterport. And Matterport allows you to actually use your cell phone to make a 3D representation of your room. You have a device you can put your cell phone on and it will turn around the room. Make an accurate representation of your room, or you can actually use some of their cameras which have LiDAR in it to build an accurate representation of the environment. Then all the data goes into their 3D platform, and they can build different applications on top of that. For example, if you want to do a virtual walkthrough for a particular environment. You can also tag your objects that there are in this 3D environment. And by that tagging, it's easy then, for example, to connect it to AWS IoT TwinMaker. Now, what you see here is an environment that has been scanned by Matterport. You can go in there, and you can look at the different devices that are in there, and actually click on them and get the accurate state of the device in real time. You do this by actually combining Matterport with, by the way, it's just Grafana, the one that we all love to use. So you have all of this fusion of models and sensors and data that is all coming together. But you know what? It is not enough. Yeah, because there is something that we humans can do that is actually pretty tricky in a digital world. If you have ever tried to put suitcases in your car, yeah, thinking in 2D won't help you. Yeah? You really need a good sense of 3D to be able to stack all these suitcases in your car. You need what's called spatial intelligence. Now, most of us have this, not all. Yeah? And so it helps humans understand the physical world through a digital lens. And the world is made up of lots of these digital objects, and we have to understand how they relate to each other. And for that, we need spatial intelligence. If you think about maps, maps are pervasive. We all use them. They're really good how to get from A to B. By the way, they're two-dimensional. So they're not really an accurate representation of the world. I know we were on a road trip once in Croatia, and the map told us that, yes, we could go through that street, but it didn't tell me how wide the street was. Believe me, backing out of that street was a major adventure. Yeah? And if you're driving a truck, you may want to know how to get from A to B, but you also need to know the height of the overpasses to be able to make sure that you can actually drive underneath them. And especially in a world like, for example, autonomous driving, these simple 2D maps are not enough. You should think about maps as being layered, as different time frames. Roads probably won't change for years. Lanes on them may change on a yearly basis. Then you may have roadworks that take for months, or stalled cars that are actually there on an hourly or daily basis. You need to have all of that information if you want to build things like autonomous driving cars. And so one of these examples is, for example, Zoox. Zoox are building a fleet of autonomous vehicles to serve as ride-hail sharing. And in the city, of course, there's lots of dynamic aspects. And Zoox is able to predict the trajectory of vehicles, of people, and even animals around them, and so they can make sensible and safe driving decisions. These vehicles need to have spatial intelligence, and it requires a fusion of sensors and custom ML models. And the perception system has this data that comes from, I think, cameras and LiDAR and infrared radar and things like that. And all these sensors together...
This LiDAR stuff is cool. I don't have any use cases, so...
Now, here you see the visualization of it.
All right, let's move on.
Use that visualization. Maps need to be software accessible for these systems to work, not just visual. We, however, we like to visualize. And we want to visualize actually everything that we can think of. Even in our consoles, we love to visualize the state of our system. Systems don't need visualization by themselves. They're all for us. Humans need to visualize these things. And I think a company that understands this challenge best is Epic Games. And please welcome Nathan Thomas, the VP of Unreal Engine, to show how their technology is being used to create the experiences of the future. Nathan.
again, it's great to be here today at reInvent. I'd like to talk a little bit with you today about Unreal Engine, which is the game engine that we use to build our own games like Fortnite, and which we make available to thousands of game developers around the world to build everything from small independent games to the biggest AAA titles that we all know and love. Unreal Engine is built by creators for creators. It's a really important symbiotic relationship where we can drive innovation into the engine through our own game development and then make that available to the folks using Unreal Engine. Over the last few years, we've really focused on increasing the level of photorealism and cinematics in Engine, which has helped it really go beyond games into a wide range of additional industries. We're seeing users lead a real-time 3D revolution through their own creativity applied to our tools. They're doing all kinds of things we couldn't have even imagined were possible. Now, Unreal Engine is part of that story. Our tools like MetaHuman, Twinmotion, and Reality Scan are another part of that story that are really helping us make it easier than ever to build and share real-time 3D experiences. So I'll be talking a little bit about those as well. Now, of course, all of these tools use AWS in their development and operations, which helps gives us the flexibility and scale that we need to grow. Now, when you're building the world's most innovative game engine, you don't get there just by launching a grab bag of features. You've got to use that technology yourself to build experiences that push the limits and demonstrate what's possible. That's why we built the Matrix Awakens, an Unreal Engine 5 experience. This is a large-scale, photorealistic, open-world environment. It's dynamic and AI-driven, and it really shows the limitless storytelling possibilities of Unreal Engine 5. And we shipped it on next-generation consoles like the PS5 and Xbox X to show you can get this level of fidelity in real time on hardware that's available today. The world is pretty impressive. It's about 16 kilometers. It's got 40,000 cars that are drivable and destructible. It's got about 35,000 metahuman pedestrians wandering around. It's about 7,000 buildings, and it's billions of polygons. And a lot of this is procedurally generated by Houdini, which means that it's a lot easier on artist workload. It's a logically consistent and believable world. And we really believe it represents the underpinnings of a lot of the future of the 3D experiences we're all going to have together. Historically, this type of large-scale open-world creation for 3D generation is challenging. And Unreal Engine is solving that in a lot of ways. But as I said, Unreal Engine is only part of the story here. For one thing, you're going to want to put characters into that world that you're building. So we launched MetaHuman Creator, an online web service which allows you to generate high-fidelity digital humans in minutes, and those are free for use in Unreal Engine. This is something that used to cost millions of dollars to do. We use EC2 GPU instances to help us do the data processing, moving from petabytes of back-end data down to hundreds of gigabytes running on instances, and then down to a mesh you can export to Unreal Engine. And of course, when we did that, we needed data protection, and we needed instant availability and a high-quality user experience. So we're using pixel streaming to get those properties. That really lets us reach our users at scale. And of course, that high-quality experience and scale has helped make it a huge hit. We've seen over 2 million metahumans created to date. And to give you an idea, if you go back to 2017, we estimate there were maybe 75,000 of these in production. So we're seeing a massive uptake based on the availability of this service. Now, also, as you develop your experience, you're going to want to share, and you're going to want to collaborate on it. And so Twinmotion is our 3D visualization tool built on top of Unreal Engine with a simpler interface. It lets you share high-quality images, panoramas, and 360-degree videos. And on top of that, we built Twinmotion Cloud, which is a web service running on AWS that lets you stream interactive experiences. And share it in a browser, which means that you don't have to have any additional hardware or any additional software installed. And like MetaHuman Creator, this is running on EC2 GPU instances, G4 and G5 in this case. This really allows us to get the high engagement that we want from the highest need projects, which need things like G5 instances, while still supporting G4 instances for projects that don't need that much hardware and saving some money. And then, of course, you're also going to want your experiences you're building to have the highest quality assets and environments inside of them. So photogrammetry is the art and science of creating 3D assets from 2D images instead of creating them by hand. Much simpler, much faster, and higher quality. The gold standard for this has been Epic's desktop application, Reality Capture, which really makes it simple to create those ultra-realistic models from images. Reality Scan is our new phone application that brings that same incredible pipeline to smartphones. It uses AWS for processing on the back end to help us generate a point cloud and a preview mesh so that it's easy for you to figure out if you're building the right set of images to get a high-quality asset. And then at the end, that asset that you're building can be shared in Sketchfab, our environment for sharing collaboratively.
Wow.
In private beta, we've had over 100,000.
It's really hard to imagine that, you know, this silly game that I used to like
and we've seen this
link up like 6 computers with my friends to go shoot them in the head has turned into this.
We use S3 and CloudFront for file storage. We do all of the processing on G4 instances, and then we use Elasticache for an accelerated experience. We've seen some really exciting high-quality models in beta, but I'm really excited to announce today that we are publicly launching Reality Scan on iOS.
If I can feed that into AutoCAD, then...
So Android will follow soon, but I encourage you to download and give this a shot now. The combination of the innovation of driving an Unreal Engine and these other tools has really helped the outputs become almost indistinguishable from reality. This is really bridging the uncanny valley and unlocking a huge range of new use cases for these tools. Like Project Antoinette, you see here, which is a new set of tools for creating flight simulation on top of Unreal Engine. We're seeing an increasing number of new sim types coming out, augmented reality, non-motion sims, and it's really helping increase the number of training hours available in the aviation industry, which is really critical. We are incredibly excited for this real-time 3D future that we can see in front of us. But that transformation is not going to happen without you, all of the innovators who are going to push this technology to its limit, which is why so much of the tech I'm describing today is free for a wide range of use cases. For example, the city sample, based on the Matrix Awakens and Unreal 5 engine experience, is available for download today. AWS Ambit Scenario Designer is another great starting point. So you can use that to jumpstart your simulation applications built on top of Unreal Engine. Our mission at Epic is to empower a new generation of creators. We really want to see you push the limits of the experiences that we can have in ways that we really can't even imagine. You have that power, the power to bring people together and to bridge imagination with real life. If you're curious about that and excited about it, I invite you to jump in right away. Thank you so much.
Goodbye.
So while Reality Scan is available today, it's a very limited beta.
So what am I scanning? Just reality? Why do I need it?
Well, I mean, the use case that you kind of saw in the video was he was scanning a tree stump and then adding it to his video game, right? I want to scan things so that I can print them like 3D printing. So replacing that battery cover on that ancient remote.
Absolutely mind-blowing. You know, our digital systems may not need visualization, but we definitely need. And what he's showing is just amazing. Actually, one of the things that Nathan mentioned was Ambit. And I really would like you to make you aware of this because it's something that you can get started with today immediately. I love Ambit. Again, it's one of these things that makes our work so much easier. So the AWS Ambit Scenario Designer is a set of open source tools that is available on GitHub that allows you to create 3D content at scale by just a click of a few buttons. So the first functionality of that is world generation, you know, the 3D environment that you need. They make it easy. You just point to a city in OpenStreetMaps and immediately Ambit will create this 3D world out of the data in OpenStreetMaps. You don't need to do anything for that. It blows my mind every time I try that. And then what you can do is you can place obstacles in that world. And you can use rules for that, how these obstacles should be placed or how they should evolve over certain parameters. And then you can add environmental effects to it. Do you want daylight, night, weather patterns, things like that. All of these different kind of scenarios you can actually add to it. And then, with one click of a button, it can generate scenarios for you. And these scenarios, they can be JSON or JTLF, and you can then import that into any of your popular simulation or visualization tools. And actually, you can set a set of parameters in scenario generation that it can literally generate thousands of different scenarios. You can immediately in your simulation
I've never heard of it.
or in your visualization. Now, as always, I think, you think about innovation. I love this particular pattern, which is in the fundamentals of Amazon. If you go back to the 1997 letter to shareholders that Jeff Bezos wrote, this is key in it. We will continuously experiment, we will measure, we will learn.
That's what they do in ML too.
And learn means that whether it's positive or negative, you need to learn. But you also need to be able to experiment. And of course, experimentation in retail is easy. We always decided that we would bring things in front of our customers. They're allowed to vote with their feet. Doesn't work out. We'll start over. But most important from that, be able to experiment, measure, and learn. Now, at larger scale, especially in a world where you can maybe not immediately manipulate the real world, simulation is key. And there's all sorts of companies that are using simulation today for many different scenarios. But it all started actually very long ago. In 200 BC, Roman generals were given wooden swords to their fighters to simulate battles and test all sorts of different strategies. And then much later, Leonardo da Vinci, the amazing innovator, actually started building small-scale models first of his innovations before he started building them. In our world, in our digital world, the pioneers of simulation have been von Neumann and Ullmann. They were two mathematicians who pioneered simulation in the digital world. And they used mathematical models to understand behavior of Newtons, for example. This was the world's first computer simulation. They're also the inventors of the Monte Carlo simulation. Monte Carlo simulation, the name already says it. You can model risk in casinos. Seriously. Of course, now it's being used for much of financial risk modeling way beyond the casino. But it was one of the first simulations that was built. Very primitive, but it worked really well. And if we get to closer into the world in the 2000s, with
are we simulating again?
Workstations and desktops with the latest hardware. But most of these simulations were sort of limited to the hardware that it would run on and the memory that you would have available. And there's such many different types of simulations were being built. Almost every vertical has their own type of simulation, and whether that's in life sciences to do drug discovery, financial services, risk modeling, oil and gas that actually takes seismic data in and then do all sorts of modeling on top of that. And we have many of our partners actually that have systems that run on AWS that provide this kind of simulations to their particular customers. And take, for example, a company like Ansys. They have specialized simulation software for engineering companies, civil engineering companies. And many of the students that actually take civil engineering, this is where they build their systems in. And so this is sort of the state of the art today. And so why do we simulate? What is the reason for simulation? Well, first of all, there are just physical limitations that you can't play with in real life. If you think about sort of a very large city, if you think about how traffic moves through that, and you want to change how that traffic moves, it's not something you're going to do in real life, and just try and figure it out. For example,
in crazy things.
COVID pandemic.
Today marks 4 years since we came up with the idea for the Cloud Pod at reInvent.
Wow. Yeah.
During the Werner
Crazy.
Keynote. Like, we should do a podcast. We were drunk at the time. And now we're here, 190 episodes in, so.
Yeah.
Congratulations.
Yet another fine product of drinking.
Simulation
Yeah.
has three dimensions because they have to simulate the real world. And if I think about how I learned geography, I learned them from atlas, and I was mesmerized. I would dream about faraway countries and hills and things like that. But the atlases in reality were 2D. I was still amazed by it. Today, kids learn geography by flying through the simulated 3D world. They can see around them how high the Mount Everest is, or they can see the tigers in Nepal. All these kind of things are possible in the world of simulation. And you do this in cases where, of course, you can't.
This is dangerously close to metaverse talk.
Yeah. And
for me. I'm like,
we're sort of in this
please
area
don't go into. Yeah.
It's cutting edge. I get it's cool. I get people care about it. It's just,
where you don't want to try these out in real life. Yeah? And so, for example, many of the autonomous cars these days that we see on the roads, or where we see these companies being built around, all use simulation. Yeah, so, for example, Aurora is one of these companies that are building technology for autonomous trucking. And they use LiDAR and cameras and radars to see hundreds of meters in front of them. But they are crucial using this information in simulation. Because you can't just do messing around with the real world with trucks, because that would be seriously hazardous. And so, for example, their system performed over 2 million unprotected left-hand turns virtually before it did one in the real world. And then the other reason, one of the other reasons for simulation is that you can manipulate the fourth dimension, that of time. Yeah? And in essence, it can millions of simulations in parallel, doing years of testing in just hours. Here you see the deforestation of in Bolivia happening, and of course this happens over decades. Not just in seconds, but in simulation, you can speed up time to see the results of things that would normally take years and years and years to complete. And so you can speed up time, or slow it down. You want to get a much more fine-grained control. But there's another type of simulation where we want to look at today, and that's that of spatial simulation. Yeah? So the real world around us is enormously complex. There's thousands of events and there's thousands of entities continuously around it. Think about urban traffic. There's hundreds of thousands of instances. Think about, there's this big football game going on and a pop concert not far away from that. How does traffic go through the city to reach that? How do you manipulate that? What do you have to do to make all of that safe? Yeah?
I'm currently navigating my house on crutches, so, spatial awareness is a thing. Turns out 3 kids and crutches, not a good mix.
Behavior, interaction behavior. And we used to run these type of simulations on a single machine because it requires a significant amount of memory to be able to do this. Because the large number of simulations, the large number of entities take up a lot of memory. And especially how they are moving through the space. And Adam, on Tuesday, already announced SimSpace Weaver. And I want to dive a little bit deeper into this with you.
Covering SimSpace Weaver again, huh?
SimSpace Weaver
He's like, Swami didn't cover it well enough. I need to talk about it more. Or was it Adam who talked about it?
It was Adam, yeah.
So
it's all a blur at this point. By Thursday, every event week, I'm just numb. I was looking at the RSS feed earlier for all the stuff, AWS news blog, official blogs, 59, and then the What's New blog, which is all the small stuff, 124.
That's a lot.
Yeah. But Google at least stayed out of it. They only announced 8 things this week, and I don't think anything's actually they have a couple of new things, but it's mostly like customer stories. And, they do a lot of how-to blog posts. And then Azure had 2 stories, so they at least stayed out of it this week as much as they could. Oracle, typical, but nothing interesting enough to talk about.
Or they broke the RSS feed, right?
Well, they fixed it back. I don't know.
Oh, they did? Yeah, okay.
Where do you plant your seeds? What type of trees should we plant here? How much carbon capture is actually happening over the year? And can we encourage biodiversity? Because it turns out that biodiversity is extremely important for the health of an ecosystem. And you need to consider where seeds are, what type of seeds, where you source your plants from, the density, the planting method, how far away from each other, and what kind of impact this forest will have on wildlife, and what impact wildlife has on the forest. And so let's start off.
If you don't show me an architecture diagram soon, I'm going to fade.
This is a piece of barren land. And so this is a huge space.
Oh, he's getting comfortable.
Hundreds of thousands of trees and plants. So a simulation is, imagine we would take this area as a simulation. And this is many miles, actually. So we divide it up in a grid. And in a simulation, we may ask questions like, where might be the best place to plant our seeds to achieve the best biodiversity and overall growth? What if we planted here? The simulation is then able to speed up, and we can see the future. Because it's just in a simulation, and we can experiment. Imagine you would start in a different area. Imagine what would happen if you start here. You see that the trees will grow in a very different pattern, mostly because the water around it, it supports it and actually also helps with germination. And every object in our simulation is a separate entity. And some of these entities move and interact with the environment. Trees don't move, of course. Yeah? But our simulation shows how germination happens, how the seeds travel throughout the world. And what makes SimSpace Weaver unique is how this simulation is distributed. Our spatial simulation is broken up into a grid. The simulation logic operates on each of the individual cells in the grid. Each cell tracks a logic for that area and for all the entities in that cell. And every object is a separate entity, the trees, the seeds, the animals. And the cells are distributed about a cluster of computing instances. These instances work together to process the entire simulation as if you have one very large memory model. And it appears as a single integrated space with everything in it. And you have clients that can connect to it and visualize it like we do here. And SimSpace Weaver handles all the networking, it handles the memory management, it handles the synchronization. All of that is being done for you. All the heavy lifting that you would need to do for spatial simulation is handled by SimSpace Weaver. Now, we can track millions of entities. The trees, the shrubs, the wildlife, the deer, and birds, they're all entities. Animals cross boundaries in the grid. Yeah? And as they cross boundaries, they're actually transported to other cells in the grid. They are actually really being transferred. And it appears that trees are actually not growing in the middle part. And I honestly think that that's because of the deer. I've lived in an environment with lots of deer. They eat everything. And so it appears that trees are not growing. And it might be because indeed the deer are eating the captain. So what would happen if we would build a fence there? You see then that sort of north trees will grow because the fence is there and the deer no longer has any impact on it. These are things that are not easy to try in real life. Trees may take 50 years to grow. Simulation is a true representation here of what would happen in real life if you would actually take this approach. And this is just one way a company like Terraformation could use simulation. So what are other things that you could simulate? What are the other things? Now you can simulate...
We're talking about simulation, I tuned out for a second.
Traffic patterns.
Yeah.
Transportation network.
I'm struggling to keep on top of this.
The millions of entities in this spatial intelligent world.
Usually I fade at this time of his keynotes, but I'm usually way more hungover, so I've been blaming that, but now...
I think simulation plays a crucial role in innovation. Because you can play for all these what-if scenarios, even with the digital systems, that you can't do in real life. And you can experiment as much as you want without actually having impact on the real world before you take out your systems to the real world. And I think there is a true pattern happening where the border between digital systems and the physical real world is slowly disappearing. Now, we've already seen that with Alexa. Many of our customers don't realize that behind Alexa is a complex distributed system. And so this is becoming vague. And as such, the more of us that actually build systems that need to act with the real world, simulation is crucial there. Now, what about the future? What is simulation really the magic key to build systems in the future? Now, it helps us understand, of course, the laws of reality underneath. But these simulations, despite being highly realistic, with complicated physics engines, they're just approximations. They will get more complex and more realistic over time, but still, there will be a lot of unsolvable problems. Take, for example, if you wanted to simulate very small things, like the configuration of molecules, the computational effort needed scales exponentially with the number of models in your simulation. Today, we often use Monte Carlo simulations or DFTs to simulate the behavior of molecules. And they're incredibly helpful and successful in helping us understand the world, but there's still significant approximations of the real world. Now, given that we are living in a simulation as well, I can now easily fast forward 20 years. Yeah? What if you wanted to simulate without using approximation? You would need a lot more memory actually than exists in the world. But this is only a problem with the computers of 20 years ago, or our current computers. Yeah? What might be possible with quantum computing in 10 or 20 years from now. Quantum-based chemistry simulations are not as accurate today as our supercomputers are, and that's because quantum hardware is still in development. But to try the state-of-the-art quantum computers, the prototypes of that, we can use AWS Bracket. There's a range of young businesses that have been building quantum computers, and they're all available through AWS Bracket for you to experiment with. The world of quantum computers doesn't have, for example, our rich set of development tools yet. What are the tools that are necessary? What is how you're thinking about algorithms in that particular world? And Bracket really allows us to democratize the access to quantum computers so that we can help innovate definitely the software side of building on quantum computers. And they have actually the ability to answer the questions that would be impossible for classic computers right now. So let's play this little test. Imagine you have a fundamental quantum object, like an electron. You need 2 bits on a current computer. For a collection of 2 electrons, you need 2 to the power 2. And for a collection of n electrons, you need 2 to the power n bits. Now, remember, if you would take, for example, a molecule of penicillin, it has 41 atoms. And to model that, you would need 285 electrons. That is 2 to the power 285 bits. That is more memory than we have available in the whole world. It's this. I'm not going to pronounce it. Now, I did put it through polling, by the way, and it took a minute to pronounce it. I'll post it somewhere, and you can figure out, what this really, really, really big number is. And so the memory you need is going to double for each new object that you add to the collection. So the memory you need is exponential. It's impossible today in our current world in the way that we build our systems. In the quantum world, however, you can represent an electron with some other quantum object, and you can manipulate that at will. You don't need this large amount of memory. A qubit is a fundamental unit of quantum information. And it can be used to encode quantum objects from your collection. For 285 fundamental objects, like electrons, you can use 285 qubits directly. And this allows us to start thinking about simulation and understanding the world without actually having to go through this approximation. Let me give you an example. A common application when you think about quantum simulation is that of producing fertilizer. Well, we would think that's a well-known process by now, yeah? We've been producing fertilizer forever. It's a process called Haber-Bosch. Unfortunately, the process uses about 2% of the world's gas to create ammonia. Now, if you've ever taken food out of your fridge and put it on the counter and forgot about it, you know that rotting food creates ammonia with no gas. Yeah? If we could simulate that process, we will be able to copy it. And this can only be solved with quantum computing because of the complexity involved in the realistic simulation of this, which really require a quantum computer. Now, I may understand that for many of you, you think you're not really familiar with quantum computing, but it is real, and it is the reality of the future. It is how we are going to build it. Now, I understand that not everybody has gotten all of the graphs of quantum computing, so I had an interview with John Prescott, who is an Amazon scholar, and he is the Richard Feynman Professor of Theoretical Physics at Caltech. And his mind is full of quantum. And the way he talks about it is even for mine mind-boggling. So I did this interview with him, and an interspersed that is sort of going back to the fundamentals of what quantum computing really is. So this is a video, you can find it on YouTube. I've done a few of these curiosity videos about really hard problems that we are tackling in AWS. And if you want to learn more about the fundamentals of quantum computing and what the realistic state of the art is right now, and what we expect it to help us with, please watch this video. But actually, don't watch it tonight. No? There's something else to do tonight. Once again, we have the #1 DJ in the world playing at our replay party, Martin Garrix. It's going to be
a little bit of FOMO on missing out on Martin Garrix, we'll say.
Yep. These are all a little drowned out. This could have been about 30 minutes shorter.
Yeah. I mean, I think
I had that feeling
there's
about
been a
every
trend
keynote.
in the last
Yeah.
5 years for Werner. I'm glad that he's added back the announcements, because for a couple years he just did the sort of high-level, impact technology in the world sort of thing for the entire keynote. But now it's a little bit of a mix, which I think is good. And while simulation's not my cup of tea, exactly, it doesn't really excite me, like I can see, I'm sure it is for someone, and if he is covering something that is, something that I'm more interested in, it is really fascinating, because he is very smart. And I like the way he thinks, and I like the way he sort of describes things out.
Why should you think about it like that? Because it is. And I ended it by showing.
And I've been using this time wisely to sort of listen, but also try to get into my Code Catalyst preview.
I hope we can all agree that we can learn from something like looking around us and observing the greatest system in existence, the universe itself. The universe itself is extremely agile. It is extremely fault-tolerant as well, and resilient and robust. We should learn from sort of the principles that we see in nature and the world around us when we start building our computer systems. I hope this talk has inspired you to build bigger, better, bolder systems much faster. With all of that, thank you, and now go build.
All right. Well, that was overall keynote this year lacking just maybe a little bit. At least in content for. I mean, like Amazon dropped so many new features this week that we were just talking about. The RSS feeds. Like they announced a ton of stuff, just not a lot in keynotes. But I do think I won the draft.
I thought Peter got didn't Peter $1 you?
No, I won because of Graviton 3E.
Oh yeah, you definitely won that.
Yeah, so
I got nothing to argue with.
We don't go to tiebreaker on that one. So.
Yeah. Oh, that's right. That's just the tiebreaker. It's the number of announcements.
Yeah.
Yeah.
I don't count.
Yeah, I don't think any of the other ones. No, because I didn't get any of mine, definitely.
Yeah. Which is kind of disappointing because you had some good ones I was hoping for. So it's yeah, the way it works sometimes.
You know, I mean, that's the way it works pretty much every year. The fact that you got one is the exception.
Yeah, no, I was excited. I was like, yeah, I got one right out the gate. So, yeah. So, yeah, I'll summarize all this stuff down into a great recap show for next week, and we'll do a live recap show maybe. I think.
Yeah.
We're talking about that 'cause we did
live. Oh,
we did it live last year for a recap show.
Okay.
Which I forgot about until I was looking at our YouTube channel. At the only other only other video we had on there was from our live recap last year. So we could probably do that again this year too. To get some people going. And so, yeah, that's the plan, I think. But yeah, thanks, Ryan. I know Jonathan had to bail for dentist appointments, but it's good seeing you. And thanks for joining us here through the live streams. See you on the show.
Yeah, well done. All right. Bye. Thanks, everybody.